Hello, everyone, and thank you for being here today. For the second session of the virtual workshop series, 3D Firearm Imaging, we are joined by presenters Todd Weller, President of Weller Forensics, and Alan Zane, a mechanical engineer in the Sensor Science Division of the National Institute of Standards and Technology. Without further delay, I will turn things over to our presenters.
Thanks, Kelsey. So I was asked to give this talk about 6 months or so ago, and the thought was for me to come in and just talk about validation and with a focus on validating 3D instruments in general, to give kind of broad guidance, thoughts, an overview of a little bit of dabbling of the standards and the work that's going on out there right now, because a lot of us are purchasing these machines, and maybe there's a little bit of hand wringing when it comes to how do I get this up and running? How do I start using it in my laboratory? So for the next half hour or so, I'm going to provide some thoughts on that. So first, when I think a lot of us feel this way, when we buy one of these instruments, we're super excited, and then we realize, oh, I have to validate this thing. And maybe for some of you, this speaks true, where we start sort of feeling, confused, overwhelmed. I'm a firearms and toolmark examiner. Where do I begin? It just kind of seems like a huge mountain, an overwhelming task. And so that's my hope, to maybe make this a little bit less scary after going through my slides here and talking about this a little bit. And then Alan can come in with a little bit more of the specifics after I talk. So first, let me start with a couple disclaimers. As I've already said, this is really meant to provide general guidance. It's certainly guided by today's current standards. For example, there's ISO 17025 and the OSAC and ASB standards that are on the OSAC registry. So those have provided me guidance and help lay a foundation for this talk. However, some requirements are still converging and not fully developed, and Alan will talk about the work that the TWIG is doing, which we can expect from that. And there's going to, the OSAC registry is kind of a living, breathing animal. So there will be more standards. For example, at OSAC, we're currently working on a VCM standard that is in draft form. And of course, I think this is obvious, but it's worth saying, a 45-minute or 40-minute talk, I cannot cover all the requirements. You can't leave today expecting to be an expert in all the requirements in the standardizations. So again, I'm just trying to demystify this, make it a little less scary. And in my opinion, there may not necessarily be a single best way to validate. When you read some of the standards, they're pretty vague and broad, and that gives us a lot of leeway on how to do this. Certainly, we may converge on some sort of consensus. The DNA world has sort of done this. SWIGDAM has converged on consensus, and that's useful. I think we'll get there. But that being said, I might give some ideas, but you might come up with something better, a more defensible, a way of achieving that goal. And so that being said, I'm not the gold standard here. I'm not saying I have the perfect solution. These are just my thoughts on this. All right, so what is validation? That's kind of this big, broad, sometimes scary topic. And I like this definition from actually the UK Forensic Science Regulator, and they have this document a guidance document on validation. So they have a nice one-sentence definition of validation, and that is the process of providing objective evidence that a method, process, or device is fit for the specific purpose intended. I think that's clean, plain language, and kind of helps put into a more tangible form of what our goal is when we start a validation study. So why validate things? I think it's fairly obvious, but let's go ahead and provide some background or foundation for validation, why we need to do it. Well, of course, there's the international standard 17025, which we should all be familiar with. And specifically 7221 says that a laboratory shall validate their methods. Okay, so this is something we need to do. Also, ASB and OSAC have published on the OSAC registry 3 standards, standards 61, 62, and 63, that speak to validation and providing some guide rails for the validation of 3D technology. And I kind of want to draw your attention to two of these, the standard 61 and standard 63. Both of these use some of the language that I'm going to be talking about today, and especially 63 talks about the implementation of technology in your laboratory. So not only does this provide guidelines, but because it's a standard, this is something potentially that auditors or even litigators might take a look at and say, well, hey, does your validation protocol conform to this standard that's on the OSAC registry? All right, so before we talk about 3D systems and firearms, I want to provide a simple, kind of silly hypothetical example. So imagine that Weller Forensics has purchased a surplus US government supercomputer, and I have decided that I'm programming this computer to crawl the internet because I want to get images of dogs. For whatever reason, it's my plan of forensic world dominance to use images of dogs. And so I've programmed this. I think I have a good computer algorithm to crawl the internet and gather images of dogs. But before filling up my hard drives with dog images, I wanted to do a validation test. So I'm going to validate my algorithm in the computer to do that purpose, that specific purpose. So how would I go about validating this instrument? Well, I think one thing obviously you need to do is provide the computer with images of dogs. So, these are dog images, and I ask my algorithm to judge it. Is this a dog or not? So I give it 100 images of dogs, and the computer correctly IDs 95 out of 100 of those dogs. So another way to state this would be 95 are positive. And so you'll see sometimes in the literature this concept of positive and negative. My best understanding is that comes from the medical diagnostic world, where you have a medical test, and is it positive for something? Is it positive for cancer? Is it positive for COVID? After COVID and the pandemic, we're all a little more familiar with even the home testing, and is the test positive or negative? So you'll often see positive. And then, of course, we didn't get 100 out of 100. So 5 of these were negative because they did not score. So that'd be incorrect negative, right? So we have 95 correct positives, correct IDs, and 5 incorrect negatives. So I kind of asked the question, is our validation complete? Are we set? Do we have 95% accuracy? Seems pretty good. Am I ready to go? Probably not. I think we also want to test it with something else, and probably non-dog images. So might consider, well, what's the opposite of dogs? Maybe we test it with images of cats. If you think about what is the purpose though, what is my computer going to be doing? Well, it's going to be crawling the internet. So it might not be provided only just cats, right? It might be looking at lots of images. So as a silly example, I found this article looking at machine vision, computer vision, and here was an algorithm trying to judge between chihuahuas and muffins. And you can see, some of these muffins kind of look like chihuahuas, and you can see maybe how a blueberry muffin might get mistaken as a chihuahua if a chihuahua is being, this is what the computer is learning. So kind of a silly example. Fortunately, in my opinion, the problem that we're dealing with is not this complex. It's much more simple. But to give an example of what the data that you put in and what you're testing with can be extremely important on your results. So let me go back to the cat example just to make things simple. And so, okay, I gave my computer 50 cat images, and it incorrectly identified 25 of those cat images as dogs. So in other words, 25 of those are false positives, right? They're falsely ID'd as dogs, and 25 are correct negatives. So what do these results end up looking like? Well, we can put the results into a table here where we have the computer calls and the ground truth. So remember we had 100 dog images, 5 of those were incorrectly negative, 95 were correct. And then we had 50 cat images or non-dog images, and we had 25 and 25. And often these results can be described as 2 metrics: sensitivity. Sensitivity is the proportion or percentage of ground truth positives that are deemed positive. And so our sensitivity for my little study here would be 95%, which would just be 95 divided by 100. And then the other metric that you often see cited is specificity, which is the percentage of ground truth negatives that are deemed negative. Sometimes referred to as the true negative rate. In Firearms and Toolmarks, this would be the correct elimination rate. And for our test, it would be 50%, because 25 out of 50 were correctly called non-dogs. So here's our results. I have a 95% sensitivity and 50% specificity. And so the question is this valid? And my answer is, well, it kind of depends. Is it fit for the specific purpose intended? Now, maybe I have essentially unlimited hard drive space, and this is enough of a differentiation. I will end up getting more dog images than non-dog images. And so this sensitivity and specificity is fit for my purpose, my needs, let's say my computer science laboratory. And since I have lots of hard drive space, I don't mind this specificity rate. Or maybe I say, you know what, that's really going to fill up. There's going to be too much manual time sorting images here, and I would need to tighten this up a little bit. And so maybe I need to go back to computer programming my algorithm and tweak the dials a little bit. So is it valid or not? There's no magic number here. It's going to depend on, is it fit for the specific purpose intended, going back to that original definition we talked about a few minutes ago. So there's a silly example to try to give a general sense of validation. What are we doing? And we're trying to provide some objective criteria and numbers for our methodology, our new method that we're putting in we want to deploy for casework. So there's, in general, the literature, the forensic literature talks about two types of validation. Alan's going to talk more about this in a little bit when he talks, but I'll just provide some general definitions. The first type of definition is what's called developmental validation. And the standards I talked about earlier has a definition for this. And this is the acquisition and evaluation of test data for the determination of the conditions and or limitations under which a novel method will achieve consistent results. And we didn't just pull this concept of developmental and a second type of validation, which we'll talk about on the next slide, out of nowhere. We actually modeled this off of the original DNA SWGDAM validation guidelines that talk about DNA analysis method validation. And they define developmental validation as acquisition of test data, and determination of conditions and limitations of a novel, new methodology for use on forensic database known or casework reference samples. The SWGDAM guidelines also say that these should be peer-reviewed, published in a peer-reviewed publication, and also other means of dissemination, such as this to the scientific community presentations, is encouraged. So that's one type of validation. And I'll say right now, it's unlikely most laboratories will be doing a full developmental validation. So this will be look to the manufacturers publishing either a study or a suite of studies to provide this foundation, or maybe a larger agency, such as, for example, one of the larger federal agencies that has a little bit more funding to provide more of this data. Or this could be a community-wide effort where a variety of smaller studies that are all combined together in one meta-analysis can provide this foundation. So there's multiple ways of getting to this. So the other type of validation would be a deployment validation. And again, our standard 63 has this defined, is that this is, you're providing developmental validated technology performs as expected within a specific laboratory organization. It involves the acquisition of test data using the proposed methods and procedures to demonstrate that the expected outcome is reproducible and achieves reliable results. So in other words, it's meant to be a smaller study. It doesn't have to be the full-born developmental, but a deployment study, you're still expected in your laboratory to perform some validation analysis to make sure the laboratory is performing the way you would expect it to, and it conforms to what you expect based on the literature that's already out there. And of course, SWGDAM also has a similar concept of internal validation. So now that we've talked about these types of validations. Let's talk a little bit more specific, maybe how you might approach this in your laboratory. So I first want to turn to this article, which was published back in 2006, that was just as these 3D surface topography instruments are starting to get some interest in the literature and the scientific community. And there's a nice diagram from this publication that I like. The reason why I like it because it helps us kind of think about the task at hand and what is the process. So most 3D systems used in the laboratory are going to be multiple steps. First, you're going to scan your evidence. It's going to be digitized in some way, and then there's some sort of analysis system that is going to perform analysis of the original cartridge case that's been virtualized. So if you think about validation, there's really two things to validate. First, there's the acquisition, or I'll call it the hardware. So you need to provide some evidence that this is being done reliably and it's up to the task at hand. And the second is the analysis, and then it has to provide some sort of data to show that the analysis system is up to the task at hand. And when you think about the analysis system, you can further subdivide that, right? So first, maybe we're using humans as the analysis system, and that would be the VCM, the virtual comparison microscopy. So rather than using a light comparison microscope, you're now using the computer screen and software to perform your comparisons. Or you could be using the algorithm being provided, whether it's NIST's CMC or one of the manufacturer's algorithm. Maybe you're using that for some sort of judgment as well. And so you can subdivide this further, and maybe your laboratory is going to end up using both of these in some form or another. Or maybe you'll only use one. But regardless, this step as part of the analysis is another way of kind of thinking about it. So let's talk first about validating the hardware and how you might go about doing this. So again, back to the original definition, provide objective evidence for the method or process for the specific purpose. Well, so, okay, what's our specific purpose? What does that hardware need to do? Well, it needs to take microscopic tool marks found on fired ammunition components and digitize them. So this is essentially what it needs to do. Take these breech face markings and turn them into a 3D rendering. So in other words, it needs to be able to measure three-dimensional microscopic features that are several microns in size that are found on a metallic surface. Okay, so how do we go about providing data to support that? Well, one example is, so in other words, we need to essentially provide some data of measurement accuracy in both lateral and depth measurements that are somewhat fairly small. So one example that I like or can be used is just example is the sinusoid reference. So what's a sinusoid? If we go back to our high school math or geometry, a sinusoid is a sine wave, and it's just a wave of certain period and height. And there you can buy a reference sinusoid, so the sinusoid of a certain height and length and period, and then you can scan this with your 3D instrument. You can then have the 3D instrument measure that and obtain some objective evidence. So two measurements from the metrology world would be the RSM, or the mean width, and the RA, which is the arithmetical mean height. So essentially what this is providing is a average measurement of the profile length. So how was the average profile length as you measure across that, and this is the average height of the profile. So this is now provides some objective data, and you can now perform a series of measurements, and this provides some sort of measure of both the lateral and vertical repeatability in a relatively small microscopic scale. And then you can take that data and put it into every QA manager's favorite QA tool, and that is a control chart. So here I have an example of a control chart looking at the mean width, the RSM, and we have a series of measurements. We have 30 measurements over a period of time. So just like how we've done with the uncertainty of, for example, barrel measurements, you would kind of pre-plan this activity, right? So you would maybe do several measurements, and you're going to do measurements over a period of time, perhaps maybe 30 days or 20 days. And Alan's going to talk a little bit more about specifics about the different experiments that the twig is going to be recommending. But once you get these measurements, you can then plot them in your control chart, and the control chart will then start giving these bounds. And if over a period of time, your control chart, the measurements are reasonably controlled and you're not seeing out of bounds controls, this provides some objective evidence that you have repeatable and controlled measurements. And if you look at the scale from this data here, we're approximately one micron of variance here. So, is this up to task? This provides some pretty strong evidence. In my opinion, we have less than a micron of variance over 30 measurements from this instrument. So, who should do these measurements? Well, Standard 61 provides some opinion that, or some guidance that, to the extent possible, a single individual should conduct all the measurements. And I'll tell you that I suspect this, in fact, I know based on conversations with other individuals, this is not necessarily a agreed upon thing. This may be a little bit controversial. So let's talk about the pros and cons of using a single individual to do these measurements. So a pro of having one positive of having a single individual do all these measurements for your initial validation. Well, you just have one person to train or perform competent. So that, less people pulling people off of casework, you can just assign one person to do these measurements. If you do this, then you limit your errors and variance to one person. So if you do have out of bound measurements or something's going wrong, your root cause analysis may be potentially easier. So you don't have to say, oh, is Joey just really bad at this? He's really sloppy. I need to train him more. If there's just one person who's doing it, then you can really get down into what is going wrong here. Obviously limits the number of examiners away from casework, and maybe the validation is done a little bit faster. So what are some cons and negatives to using a single individual? Well, not all the sources of variance are initially going to be captured. And this is potentially problematic because if you then start to bring the instrument online and you continue to track your measurements using a control chart, maybe your single person is really, really good at doing these measurements, and the other examiners haven't been fully trained. They're not, they're just a little bit more sloppy with their measurements, which is certainly can be something that happens. And because you have really tight variance, like you have here in this example, as you incorporate new examiners, you might start getting out of bounds measurements. It's just because you didn't capture that variance in your initial experience. Another is that using only a single individual, maybe it's good to train everyone up front, make everyone competent up front, rather than staggering the training. So maybe the ultimate adoption of the technology is slower. So this is kind of an open question and another potential negative of doing it this way. All right, what about validating the software? So we'll go back to our original definition, and I'll give two examples. First, we'll talk about using the algorithm. One example of using the algorithm, maybe you're going to use the algorithm for some sort of triage, some sort of initial screening. Well, you might ask the question, well, what's your current methodology? Because that's what you're going to be comparing it to. So for example, you might just be having a technician sort by class characteristics. So that's what you're going to be comparing to, the methodology. And then you need to assess the triage algorithm with casework-like samples. And the OSAC or ASB Standard 62 provides some guidance on that, talking about to guard against overfitting, and to prove the likelihood of performance, you should try to use a variety of substrate types and make the validation to be what you expect in casework. So how do you go about finding casework examples and make it look like casework? So obviously you're going to try to pick a variety of calibers, makes and models, and also vary the ammunition as well for your study. There's going to be no defined number of samples to use. When I've asked statisticians, hey, how many samples should we use? They won't give, in my experience, they won't give you a number. The more the better, but there's no magic number. And Alan is going to speak more about this in a little bit. And certainly we can ask questions at the end, of provide a little bit more guidance on that. So this, no matter what we do, I don't think this study can be statistically perfect. You know, a statistician might say you need random sampling or other statistical concepts, but I think there is ways to make a good effort to try to make your database casework-like. VCM, thoughts on VCM. So should you test examiners with comparisons? I mean, obviously that's how you're going to get objective data. You need to provide examiners where they don't know the results, and they are asked to judge them as they would in casework. So some considerations with this. Same concept, we should use representative samples that are casework-like. How many comparisons should we be doing? Alan's going to talk more about this, but there's the concept of the rule of three, which provides some sense of what your error rate would be if no errors were detected. Should you include all of your examiners? And do all the comparisons need to be evenly balanced across all staff? So the pros of doing this, while your error rate will not be biased towards any certain staff. You know, you don't want to give your superstar, if you have some way of identifying who that is, to all of the examiners. You just have a few with someone who you might have questions about. So, and also having stuff evenly balanced means the distribution of these casework representative samples can be more evenly distributed across all the staff. Of course, the cons of doing this is you have to pull examiners from casework. And so, you know, that's the challenge of getting this type of study done. My suggestion is to just chip away at it. Don't expect to get it done in one day or 1 week. Just set block time so that you can do a couple examinations a day to chip away. How about the study design? So do you want to have independent comparisons, meaning you have one-to-ones or maybe a couple knowns compared to one? You compare those and you move on, versus a set-based where you just have a whole bunch of stuff and you ask to intercompare them. And I think it's pretty clear that the independent comparisons should be independent, and there's strong statistical reasons to do that. So in other words, no repeat or reuse of the same items for conclusions. And so here's the limitation with this type of study. Any error rate that you calculate is unlikely or may not speak to the chance of error in any given case. And why that is a much bigger discussion that's beyond the time that is for this lecture. But if there's questions about that, we can talk about it during the question and answer. So a couple examples I want to quickly pull from the literature for you guys to have a little more guidance. So if you want further reading on some validation examples, here are some examples. So first, bring up this recent article by Henry Swafford and a number of NIST individuals. And I think this is a nice example because first they have a discussion about how to treat inconclusives. So my silly example about cats and dogs, you may note, didn't talk about inconclusives. And this article provides good guidance on how to treat the inconclusives. And long story short, is just report all the data. They also have a discussion on method validation and discussion about accuracy versus reproducibility. So here's an example of two hypothetical methods, method 3 and method 4. And you can see the false positive rate here is 1% for both, but the methods are not really equal. Here we have a higher sensitivity, correct identifications, versus here, whereas method 4 has a higher specificity versus sensitivity. So it's kind of a nice general big picture article that's probably worth reading and getting better idea about method validation and some of these bigger concepts. Another paper by Swafford is talking about algorithms and the adoption of algorithms. And so one thing that's considering, I think one thing that we think about is what algorithms is essentially the algorithm being used to replace the human. And I think what we really need to focus more on initially, if you're going to start incorporating algorithm, is these earlier steps. For example, like using it for a screening tool, a triage, or some sort of quality control method. I think this is much more doable than the end game here, which is to come up with some sort of likelihood ratio or algorithm only method. Eventually, hopefully, maybe someday we'll get there, but I think categories 1 or 2 from this article is something for the community as a general to think about. And they note that in this article, we humans are very cautious about just handing over the wheel to the algorithm only. But if we integrate it as a supplement to the human decisioning, we're much more likely to trust the outcome. And I think that's the right approach. One validation study published in the literature is from Canada. Laura Knowles is the lead author. And here's a study where they compared light microscopy versus VCM. They had a way of measuring what they call complexity. Essentially, complexity is how inconclusive it is. And they concluded that with their study, that LCM is as good, if maybe not a little bit better, than VCM. I co-published an article with some of the cadre, as well as John Marshall from Canada. And here we did kind of a classic error rate study, give examiners knowns and unknowns, and publish our results. We also included these heat maps to get a sense of consensus or not of what surfaces examiners were using for their study. So to wrap up here, how do we get started? How do we get started on a validation? Well, the first step is install and set up your system. That's fairly obvious, but you're going to have the initial setup, and the manufacturer should provide some assurance that it is working properly. Then you should or shall assign a validation manager. Ultimately, there should be one person that is responsible for the validation. And this person should have appropriate firearms and laboratory knowledge to complete the task at hand. In the world of forensic auditing and validation, the validation manager is typically anointed as competent in the method after completing the study. So this person, and rightfully so, after doing a validation study, is deemed competent and then can train the rest of the laboratory in it and assess other people's competency. Should perform the initial training and system familiarization that the manufacturer recommends, and even perhaps kind of playing with the instrument yourself. Get familiar with it. Start to kind of learn how it works before you get going on your validation study. Get familiar with the instrument. Then before doing the validation study, you need to draft your validation study. This is a pre-planned activity, so you should have a study fairly detailed. And ultimately, if you're going through the validation study and say, oh, I should really do this, or can supplement the study, you can change the validation plan. So come up with the change, but drafting that initial plan, I think, is really crucial step. And then ultimately, you need to judge your study. So you have to come up with some successful data. So for example, in triage, you can take a look at the sensitivity, and is it fairly reasonable and as good or not better than current methodology. So one thing to think about with sensitivity is total sensitivity versus grouping sensitivity. And what do I mean by that? So you can imagine if you have 4 items that you're comparing. Total sensitivity is there's 6 total different comparisons. If you look at 4, if you intercompare all 4 of those items, there's 6 comparisons that can happen. So I might have only 3 matches. So my total sensitivity might be 50%. But those 3 matches might happen to link up all 4 of those items. So my grouping sensitivity could be 100%, but the total sensitivity is 50%. So something to consider there if you're looking at a triage type method. Also, you may also consider the downstream effects of, for example, having samples ready in VCM for later confirmations. Maybe that's a benefit that can say that, okay, may not be quite as fast or is equally as fast as my current methodology, but this benefit helps in the long run our methodology. For VCM, ideally you'd have no false positives. Obviously, you do root cause analysis of any errors. Maybe there's a sample swap, some sort of measurement error. So something to look into if you do have errors. So one example of actual data from a triage study that I helped the laboratory with. So the laboratory was using class characteristics. And so we made a database or a test set that were representative casework. Where did we get that data from? We actually used a laboratory database, their own data. It was just NIBIN of prior casework stats. And then so that provided a guide of what makes, models, and calibers to use that's going to mimic what the laboratory typically sees in casework. So as a result, we ended up performing 500 known matches and over 14,000 known non-match comparisons. And this is the distribution of scores that we obtained from this study. And if you look at the data, 88% of the known matches score higher than the threshold of 0.1, and 99.75% of the known non-matches score less than 0.1. So this provided support for a triage methodology that most of the time, based on the study, the expectation is this is going to properly sort the samples between matches and known matches and correctly find matches if they're fairly well marked. So post-validation, so from your validation, your report should define the limitations of the procedure. It should define the conditions under which reliable results can be obtained, and then also talk about the aspects of the procedure that must be controlled or monitored. And Alan's going to talk more about that. And then the ability of the performance of the procedure. Obviously, you can provide that data, the objective data. And from there, you'll write your protocols and then do some proficiency testing and then ongoing competency testing. And then your ongoing performance checks. I believe Alan's going to talk about the frequency of the checks and how often you should do that. So that's my quick overview of validation, trying to make this a little less foggy. And from there, I'm going to hand over to Alan.
Thanks, Todd. Get this up. All right, I believe you guys are seeing the slides right now. So hello again. I guess all of you guys were here last week, so you already know me. But today what I'm going to do is follow up Todd's talk about validation and discuss what we're doing in the technical working group for 3D Toolmark technologies. Essentially what this group is going to be doing is writing best practices and procedures about how to do some of that validation as well as tracking the quality as we move forward. So same disclaimer as last week. We're going to mention any commercial entities, doesn't imply any kind of endorsement on our part. So the twig has been around for quite a bit now, probably close to 5 years or so. In the beginning, it was just a ragtag group of examiners and researchers like myself got together and started talking about maybe we should come up with some procedures. Because while working with the OSAC, we were kind of handcuffed to not making specific procedures that'll just get stuck in review and everyone's got their opinion about how to validate. So we made very broad, high-level recommendations to say, hey, you got to validate this using diverse samples, et cetera, but we didn't actually go into detail about how to do that or even provide resources of helping laboratories like yourselves to even run it. So the twig was formed in an effort to address that particular gap. And it's sponsored by NIJ and RTI, of course. And again, we want to write consensus-based standards, guidelines, and best practices, and even just recommendations. So this group actually follows the same procedures like any other SDO out there. We draft a standard, it gets voted out of our twig, goes for public comments, comes back, we adjudicate those comments, and then anyone who commented has a chance to appeal. So it's the entire process of a regular standard. But what this allows us to do is be more agile. So if a new technology pops up, we can easily evaluate it. We can see if our current standards are still relevant and make changes and additions as we go in a relatively faster process. So within the twigs, we have the following task groups. And we are an international group. Most of the people here are in the United States. We have 19 or so voting members right now. We have 7 international members. We have a whole bunch of other associate members as well who join the meetings and provide their input. But the most active ones are the quality assurance and the deployment validation assessment task groups. So the first 2 documents we decided to tackle are here. So the first one is Best Practices Guide for Calibration and Quality Control of 3D Surface Topography Measurement Instruments used for virtual comparison microscopy of toolmarks. Extremely long title. But we looked at instruments that are out there right now and tried to figure out a single set of procedures to help track quality across all the instruments that are available to the laboratories out there. And this ended up being much harder than you would expect. which is why it actually took quite a bit of discussion and time to develop it. So the scope of this first document is, of course, once you get that instrument, like Todd says, how do you get it operational? What kind of calibrations, what kind of verifications, how do you monitor quality assurance? And some of this information you might have seen last week from Rachel's presentation, but a lot of this is just the workflow from getting that instrument to running your validation to day-to-day work. And the workflow is simply this, and this is what we're proposing. So your instrument obviously comes from a vendor, and that particular vendor at the factory, they're going to do a quality check and they're going to make sure the instrument's ready to go before they ship it to you. And then once it's in your laboratory, they're going to install it. And of course, again, run a calibration, check their manufacturer spec, make sure it's still operating correctly. Not only from the shipping process, but also is your environment suitable for their manufacturer specs, right? And everything's ready to go. They check off. You get a nice certificate that says that instrument's good to go. You can use it for your validation and your casework. So here's what we call that instrument, what we term calibrated state, which just means that that instrument is under manufacturer specs, and it's going to be as good as it's going to be from now on. And what we're proposing is that you as a laboratory take that calibrated state and take advantage of that calibrated state, do all of your training and all of your control charting at the very beginning of that, because you want to be as close to that calibrated state as possible. And part of that involves developing your control charts, which we'll get into in the following slides, using check standards like Rachel was talking about last week with primary and backup check standards. It could be our SRMs, or it could just be reference samples you have in your laboratory that you choose as the master. And the way to develop these control charts to track your performance, and when I say performance here, you're simply trying to detect change from that calibrated state. So if you develop your control chart in the state that that instrument is going to be as good as it's going to be, then you know how much variation there is from day to day, from personnel to personnel. And what you're looking for is any change from that calibrated state. So like we mentioned last week, again, we have a minimum of 20 reproducibility measurements. And reproducibility measurement means typically we like you to do it on a daily basis, meaning you come in, you set the sample up, you run the measurement, take the sample off, next day you do the same thing. Because what we're trying to sample here is day-to-day variations in your environment, the user, how you set things up, and the measurement system itself. We want to capture as much of that variability as possible so that we don't make those controls extremely tight where you're always bouncing off the limits. And we also don't want to make them too loose where you could be getting erroneous measurements and you won't even know it. And especially when you have multiple people taking measurements, we want each person to take a minimum of 10 measurements per person. And we would like it to be done within a 45-day calendar period. Now, obviously, some have looked at this number and going, that's not feasible. It's not a hard wall, but we would like you guys to try to do it as close to that installation date as possible, because we want to make sure that that instrument isn't going to be changing or something happens to the instrument before you run your control charts. And of course, another minimum is also to span it over 10 days, just to make sure that we're capturing day-to-day variations. Sometimes your laboratories aren't well controlled. Sometimes there's a lot of vibrations going on with some sort of air handling. We want to capture all of that variation. Once you have the data, the twig also provides templates for these kind of control charts. So these are actually directly from the template themselves. And what you're doing is, so this first 20 data points here is what you call the gauge reproducibility data. Using these 20 data points, you are establishing these control limits, the lower warning limit and the lower control limit. Now, this is a one-sided control chart. So this is for things like a similarity metric. For example, if you use a bulleted cartridge case and your system comes with a similarity metric, you would run that on a daily basis or whatever your cycle is, to track to see if there's any changes to that similarity. Now, if you're using more geometric standards, you don't really have a upper limit or only a lower limit, because a step height, for example, if you're trying to measure a step height for the Z-scale, your instrument could measure it much lower or much higher, right? So you want control limits on both because you want it to be right in the middle. So we also provide a control chart for that as well. Same kind of concept. You have yellow warning limits and red control limits. Now, of course, the control limits, the red lines are the go, no go for your daily stuff. Warning limits is just maybe we should check it, make sure everything's okay before we move forward. Now, one thing I mentioned is the use of a similarity score for tracking control. Now, it may sound pretty straightforward, but it's not always that straightforward because the similarity metric has to be sensitive to scaled errors, meaning your X and Y and your Z scales for your 3D measurements. Any errors in that, we need to make sure that your similarity metric is sensitive to it. So if there is a change, you do see a drift into that score. And one thing we did as well, and anytime you see this little logo up here is what the twig will be providing you. So we also provide a set of data that you can run into your system. Let's say you purchase an Evo or Cadre system or Quantum system. You can download this data set and run the set of test data to see whether or not your similarity metric is sensitive. So what that means is we provide data that's deliberately scaled erroneously in the X and Y and Z scales, and you can actually test the algorithm. So you can see here, if there's no error at all, you should get 100% for this metric. And as you start increasing and decreasing the scale right here, you should see a drop in your score, right? That means you can actually detect any kind of changes. Same thing for the Z, there's things like the root mean square roughness you can calculate, and you can see that as you change the scale on purpose, in this case, you should see a degradation. So the whole point here is to detect any change from the time that instrument was installed and deemed operational. Now, just like Rachel mentioned last week, how often you do your checks, and let's go back to the control chart here. So after these first 20 data points, you have now established these boundaries and control limits. Now, everything after that is your routine quality control check data. And how often you do that is, technically we're leaving it to the laboratories, but we encourage you to do it frequently. And I think last week, Michelle said that they do it every day, that they take an actual casework measurement, which to me is the optimal way to do it because you don't want to lose any data in between, but you also want to make sure that you're fully confident that everything's in operation when you took that casework evidence measurements. But again, the three different scenarios, if you only do 5 scans in between your quality control checks and the quality control check fails, then you only lose those 5 scans. You go back and you remeasure them. But if you span it out to 15 or 20 scans or over 20 days or whatever, then you may be losing a lot of data. You have no idea where this error occurred and whether that data is still useful. And the scarier one is, let's say temperature went out in your laboratory for over a couple of days, but you're still taking measurements or something. You don't know if that data is good unless you're doing a quality check. Maybe the temperature came back and your quality check is green again, but then you may have some erroneous data in between. So the general message is try to do this frequently for the quality control checks. As part of the document, we also provide this flow chart. It's like a decision process for you to walk through. But we separate into 3 different stages. The green is the validation stage for that particular piece of hardware. We have the usage and then the diagnostic side of things. So you install the instrument, it's calibrated and it's verified, and then you have your control chart. You develop your control charts here. And the next step, after control chart's ready to go, you're taking data for your VCM validation, right? The VCM validation is the cornerstone of not only the hardware side of things, but also the software and the VCM and human examiner conclusions. Because what we're trying to demonstrate here is that under those conditions, meaning your control chart, your hardware in the calibrated state, if you successfully pass the VCM validation, then that means that particular system is validated for that purpose. Now, if you don't pass the VCM validation, obviously you got to go back and root cause analysis, just like Todd says, to see if it's an examiner issue. And if it's yes, then retrain them and run it again. If it's not, then you got to see if it's a procedures or maybe it's an instrument issue. So you can kind of follow this chart to go through and figure out what the next steps are when something goes awry. But if you do pass, you go into VCM and casework. And at that point, you're essentially relying on your control chart and looking for any kind of measurement concerns. Measurement concerns being you're out of control on your charts, or maybe someone spilled coffee on the instrument or something. So these are the kind of things that trigger an investigation into this system by doing what's called a conformity check. And this conformity check is basically you taking repeat measurements to see if you can get the measured value back into the control chart. If you're completely out of control all the time, then you're going to have to contact the instrument manufacturers to either diagnose or recalibrate the instrument. Then you go back to this chain again. But the document goes into more detail here. So let's now move on to VCM validation, which is a question we get a lot from a lot of laboratories, and I'm sure all of you attending today, is how do you actually validate these things and what are the procedures for it? So we have a second task group within a twig writing a document on this one. And this took a bit of discussion as well. And I think a year ago, we had an in-person meeting where this was kind of a heated topic, and you'll see why. So in virtual comparison microscopy, I took a chunk of text out of the OSAC VCM draft, the forward portion of it. So we all understand what VCM is, but again, it's what purpose are you using it for determines what kind of validation you run. Just like Todd just mentioned, he was doing a triage and class characteristic determinations, but then there's also assessing suitability, class characteristics like Todd did, performing triage, determining source conclusions, conducting remote verifications. Basically, whatever you're going to use that system for, you have to design a validation plan to test that particular set of tests and whether it's fit for purpose or not. And what you're really testing is the VCM system as a whole. When I say system, it includes hardware, the software, the personnel, proficiency of the personnel, your environment, the quality assurance procedures, basically anything that can affect your VCM itself. You need to make sure that it's part of your validation process to ensure that you can catch those kind of errors before moving forward. Now, what do you put into VCM? I really like Todd's example of just sample. If you have an IBM database within your laboratories, do a poll. See what the most common types of calibers, sample types, guns, and choose those to generate some samples within your reference collection or any access you have to either seize guns or dispo guns or whatever it is. But you want to make sure that you have enough diversity in your validation. Now, obviously, you can make a super simple test of only Glocks with really good shear marks, but that doesn't really test whether VCM works for all these other types of marks. Because one of the things you want to make sure you test is, does that system have the capability of acquiring the variety of marks that I see on a day-to-day case? Meaning gross marks, fine marks, things that mark well, things that don't mark well, and things with subclass. You want to make sure all of that is rolled into it because you want to make sure that the system, number one, is able to capture those types of marks. And then two, whether your examiners are able to use the software in viewing those marks to make the correct determination. So this is determined by almost like a case-by-case basis of what types of samples you include in your validation. Obviously, the more diverse, the better. And of course, the $1 million question is sample size. And Todd alluded to this. So we had a bunch of chats with statisticians about, well, I mean, a lot of times, you run validations, some black box studies even, they come back with 0 errors. Can you say it's a 0 error rate? Of course not. So in statistics, the rule of 3 addresses the 2 questions that are asked typically when you want to look at sample sizes. One is, what is the error rate if no errors were observed during the experiment, right? If you make 0 errors, what can you say about your error rate? Definitely you can't say 0, you just haven't sampled it enough to reach that error. Another one you can reword it is how many trials or comparisons should be conducted to estimate an error rate of something. So in a very simple formula, if you take 3 divided by the number of comparisons, you get the expected 0 to whatever % error rate you're trying to achieve. And this is summarized in this table here. So let's say in a laboratory, you want to be 95% confident that your error rate, your false positive error rate is between 0 and 1%, meaning you made no errors whatsoever, and your error is below 1%. You would need a minimum of 299 comparisons of known non-matches to be able to demonstrate that you have that kind of error rate. And of course, if you wanted to demonstrate your false negative error rate, you need to run similar numbers of no matching samples to make sure you're able to not falsely eliminate it as well. So let's say we're a little bit more lenient on the false negative side, and we say 2% error, and then 1% for the false negative. You're already looking at about 450 comparisons. 450 comparisons independently, that is 900 samples you have to measure just to create your set. Now, this is where things got heated last time during the meeting, and everyone goes, there's no way in hell a laboratory is going to have the time or resources to generate 900 comparison sets just to validate VCM. So one of the things that we discussed last time is, well, maybe the twig can help here. We want to provide data sets, almost like a seed data set that everyone here can download and then form into your validation. So we're basically giving you a head start. And currently the FBI is creating test packets. Right now, according to Rachael, we have 448 test packets prepped for both the EvoFinder and Quantum instruments. We're still in the process of getting those measured for the cadre as well. But what that means is half of them are bullets, half of them are cartridge cases. So you already start off with 224 comparisons for bullets and cartridge cases. Within that, it gets subdivided again to a third no matches and 2/3 no non-matches. But it really does give you a head start. And we want to curate this particular data set to make sure that you see a bit more diversity and you see a bit of a variety of different difficulties in the marks as well. And the data is going to be provided in native format of whatever instrument you're purchasing, if we've already measured it. And you can just simply import them, and your validation manager will go in and create these tests for your examiners. Now, the expectation is, of course, you can use this, but you also need to add your own data sets, because the important part here is you're also validating your measurement personnel and your personnel, whether they can actually use software properly, make the correct associations. But we also want to capture the types of measurements your laboratory is generating. So we want to see almost like an even mix between what we provide and what you measure. Because what you measure are going to be more focused on the typical stuff that you would see on a day-to-day basis in your casework. So you combine these, you can create your validation test sets. But again, that still seems like a lot of testing just to make sure we have the error rate. It's hard to escape. So after chatting with the statisticians even more, we came up with basically an incremental approach. And we also have a spreadsheet for this for you to develop your validation test sets. And once you fill in this spreadsheet, it'll tell you exactly what your error rate is for false positive and false negative. Even if you make an error, then it recalculates things based on that. But what we're proposing now is start your validation with some number. The twig's going to provide you a certain set of comparisons. You fill in your comparisons, and whatever that number is, let's say you only ran 100 known non-matching comparisons for your validation, then that's what you quote. If ever asked, you can quote that for this validation study, I achieved a false positive error rate between 0 and 3%. And then as you build this pool of comparisons in your validation over time, whether that's through routine proficiency testing, competency testing, then once you reach the next milestone at 150 known non-matching comparisons, then you can quote 0 to 2%. Get to 300, you can quote 0 to 1%. So this allows you, especially for the smaller labs, to slowly incrementally build up their validation for their VCM system over time without having a massive workload in the front. So now we're going to talk about an example validation that was conducted at the FBI. So at the FBI's Firearm Toolmark unit, as far as I understand and know, they were the first to validate the VCM system, and they were essentially considered the developmental validation like Todd was talking about. And at the time, they were trying to validate a cadre instrument, so they keep all of their proficiency test sets. Here's another hint to you: if you keep your proficiency test sets, those are good samples to scan in as well. From 2003 all the way to 2015 to scan everything in and basically created all these tests and sent it out to all of the examiners in their unit. And they assigned a validation manager. This could be the same manager, basically like the tech lead for your hardware, or a researcher within your unit that you can assign. But they were the ones proctoring the exams, providing the test sets, collating the data, and those kind of things. And they also included best known non-mass test sets, consecutive manufacturer test sets. And all in all, they conducted 927 comparisons. They didn't have any false IDs, but they did have one false elimination. So this obviously caused a little bit of an issue. Like Todd said, you have to establish a criteria, right? So for this one, since this is source conclusions, their criteria was any false IDs, any false eliminations is a failure for the validation. So they went back and looked at how that false elimination happened, and it turned out to be a training issue. So then they went back, retrained, and then unfortunately they had to rerun this validation again. So the next time around, they took a lot more consecutively manufactured slides, including with the proficiency tests. They reassembled the test sets, randomized everything. And this time they achieved 1,600 or so virtual comparisons. Now they've reached 0 false IDs and 0 false eliminations, which is good, right? But then when they submitted it to the FBI's scientific review board, they came back and said, well, these are all test sets and proficiency sets. What about real casework stuff? So then they actually had to go back and test the system again on old casework. So they actually went back into their history, pulled a bunch of casework out, did the measurements, and reassembled them with additional testing to show, again, that even with real casework samples, they were achieving 0 false IDs and 0 false eliminations. And interestingly enough, in one of those cases, the same examiner, mind you, in the original case made an inconclusive conclusion. And then when they used VCM, it turned into an ID. So obviously they had to deal with that internally to figure out how they were going to handle all of that. But in total, they ran over 3,000 virtual comparisons. So if you really wanted to write it down on paper, they have a 0.01 or 0 to 0.01% false positive error rate, if you want to put it that way. So one of the things I want to part with is that you shouldn't treat validation as a checkbox. It's not a binary thing where, yes, it works and you're good to go. You should consider this an ongoing check. It's a performance and proficiency test to ensure that your system is operating properly, your examiners are still using it properly, but also you're continuing to build that pool of data to demonstrate that the system works as intended and that your error rate's getting lower and lower. The more data you have, the stronger you can make your argument. Our NIST statistician usually goes, when you ask them for a sample size, they go, well, how convincing do you want to be? When you're sitting in front of a judge and jury, and they ask you, how do I know this works? Well, I ran a validation test. Well, how many comparisons do you do? I ran 50 comparisons. Not very convincing. So by using the rule of 3 and continuing to build that body of data that shows you are making correct judgment calls over time, then you can slowly start to shrink and be more convincing in your validation. And that just involves incorporating VCM tests into your lab's routine proficiency and competency testing schedule. You may have to add an additional one on an annual basis or whatever the schedule is. And not just depend on, I think I heard some labs are doing every 2 years they run a CTS test and that's all they do. You probably should do a little bit more than that, especially if you want to build more data around VCM. Maybe an annual test for your examiners, give them more comparison results or comparison tests. And one of the nice things about this is, unfortunately, for small laboratories, you have 1 or 2 examiners. Those 2 examiners will have to do quite a bit to achieve the same kind of error rates. But for a larger lab with multiple examiners, you're basically evenly spreading out the number of comparisons across your examiners. So the more examiners you have, the less each person has to do over time to reach the type of the sample size you need to demonstrate the different error rates. So one of the future priorities immediately after we meet next month. So next month when we meet, the TWIG is going to vote on the quality assurance document, and then that should go out to the public. You guys can read that in detail. And the immediate next priority for us is to write a guide on what do you do with multiple instruments. So if you're in a state system with 5 or 6 instruments of the same type, how do you create that quality infrastructure to link them all? And also some guidance on whether when you have different types of instruments, can you or should you intermingle those together or not? I mean, really the answer comes down to, if you were going to do that, you have to create a validation to test for it and make sure that the system still works as intended. So with that, that's the end of my presentation. Happy to take any questions.
All right, thank you both for providing such an informative presentation. We'll now begin the dedicated Q&A part of this presentation. If anyone in our audience has any questions, please feel free, again, raise your hand if you'd like to ask that question aloud, or you can also submit them via the Q&A pod. While we wait for any questions from our audience, again, thank you guys both for your such informative presentations. I know we do have a lot of members here who are kind of in the procurement or the very, very early stages of their validation. Having been involved in validations in the past, do you have any kind of lessons learned or tips or tricks that you might be able to share for members in that position?
Todd, you have hands-on experience. Go ahead.
Well, I'm a little hesitant to say anything because, full disclosure, the Cadre guys, including Ryan Lillian, who's the head of Cadre, is a good personal friend. And I have done validation. I have worked with validations. Some laboratories have hired me to help with their Cadre validations. That being said, I'm certainly willing to help with other manufacturer validations. But so I'm trying to just think of more general advice that is more neutral. But I have my own probably cognitive biases with giving that advice. So, but with that said, I would take any manufacturer's what their claims are with a grain of salt. They're there to sell you a product. And so I would take a look at their literature, and they're gonna have really nice pictures. They're gonna make claims about being able to scan certain things, and so I would say, okay, take that sort of with a grain of salt. I would spend booth time, the AFTI or AFS or wherever they are. Spend time with them. Often they'll have stuff there. And spend times with the software. Does the software make sense? Is it user friendly? Really try to get some hands-on time with whatever possible. Finally, I would take a look at the literature and how much literature, developmental support is there. Is there peer-reviewed published literature there to support your validation, or are you going to have to do a lot of that hand lifting? So there's a couple thoughts about kind of broader when assessing the different manufacturers and how much meat is there to back you up when it comes to making a purchase.
Yeah, and I'll second that with Todd. If you remember the first week, I had a list of like 18 or 20 different instrument specs that any 3D instrument will give you, and it's going to be confusing. And the best thing you can do is before your purchase, obviously, because remember all of this plan hinges around whether you pass your VCM validation or not. If your system can't measure an aperture shear that's too fine, it may not be a good system to even buy in the first place. So just like Todd says, go to one of these conferences, talk to the vendors, literally create a set of test samples. Go to that vendor and be like, can I measure these on your system? I want to see what the performance is. Can I still see these type of marks? We all have our best known non-match in the back of our heads or sitting in a drawer somewhere. And those are the good sets to test. You want to make sure that these systems are able to pick up the types of tool marks that you're used to seeing on a comparison scope.
Great, thank you. And Alan, I know you mentioned some of those test sets being available on the working group website. Is there any estimate, or how could our audience access some of those documents that will be forthcoming, hopefully later this fall?
Yeah, let's see. Go to the website myself. So we have a products tab on the very top, and then under that is going to be documents. Right now, there's nothing there, obviously, but yeah, by late fall, we should have that document posted so you guys can all read it. It'll also include all of our public comments and appeals and adjudication comments, just like any other standard development process. And we also have 3D training data sets right now. We have 3 of them on there. And I just had a call with Rachel this morning. We're going to put our head down and actually organize the rest of the training data sets, give them a little bit of metadata as well, and get them all posted. So the 3D training data sets are more meant for exactly what it sounds like, training people on VCM or training new examiners on these conceptually manufactured sets. There's another tab that has 3D validation test sets. Those are the ones that you're going to want to use in your validation. And I'll work with Rachel to try to put them up by the end of the year as well. I know she's got them all scanned and ready to go as far as I know. So I will work with her to get those uploaded as well. We can use them. But any information, any data sets that we come out with, they're all going to be on the website, including all the Excel templates and appendices.
Great. I think everyone will keep an eye out for some more of those documents. I know the website link has been posted in our chat for those of you here who can see that. And that is where you'll be able to access some of those documents we discussed. We have a question from the audience. What are your thoughts about smaller labs pairing up for validation together in order to meet the desired sample numbers to encourage those lower error rates?
Yeah, this also came up in discussion at our last year's when we're talking about validation and sample sizes. The short answer is complicated, where we kind of spitballed a bunch of different ideas, and statisticians just gave you a dirty look when you do. But essentially, what happens is unless your small lab and another lab or a group of labs are under the same quality umbrella, it's hard to run that validation and justify that VCM is working for you personally in your laboratory, unless you guys are going to maintain that quality infrastructure over time. So, like I said, in our next push here, we're going to be brainstorming and talking about how do we deal with multi-instrument quality assurance, because at the end of the day, it all comes down to quality assurance, because you are now trusting another lab that's not in your quality system to generate data sets to justify your own validation of VCM. If they're generating a whole bunch of trash data, you're now at risk as well. Same thing the other way around. So it's all about how much you trust the other laboratories and being able to see each other's quality assurance, seeing each other's control charts, and say, all right, I have confidence that you're measuring things properly and your system is operating properly. So let's link up and do this, but we also have to do routine measurements to ensure that we're still tracking that quality over time. So there's a bunch of different scenarios we have to play out to see where the weaknesses are. But it's not as easy as say, the state of Michigan purchases 5 instruments of the same type. Easy to do. You can link them all into one network. It gets even more complicated if you want to mix instruments like I mentioned. But yeah, we're definitely considering that, especially for those smaller labs, which is why at the interim, the easiest way is to just incrementally step up your sample size over time.
Yeah, definitely a difficult path towards partnership. Alternatively, the tiered approach, as you had mentioned.
Yeah. Now, one scenario I could imagine is laboratories sharing test fires. So you're doing all the scanning in house, but say you produce a test set of 150 test fires, you scan them in house, and then you share those at the laboratory, and they can do their own scanning of the samples. So maybe that's one where a small sharing, but so you're not sending X3P files back and forth, which really complicates things. But the initial data of just test fires, I think that would be reasonably straightforward.
Next question we have coming through is there are 2 examiners in a particular lab who are qualified to participate in the validation study. Could you go over how many comparisons would be ideal for each of the examiners in that situation where there's 2 instead of a single person in a tiered training approach?
Yeah. So in this case, like I said, whatever target error rate you want to hit in that initial validation, just split it across the 2 examiners evenly. So the more you have, the more the less each examiner will have to do. Because both of them are within your laboratory, within your quality umbrella, you can evenly split them.
And as far as like the total number of comparisons, I think the rule of 3 that Alan went over is just valuable because your validation plan will then just acknowledge up front, like, look, here's the upper bound. Maybe you can realistically, you can only do 60 known non-match comparisons to start things out. And you just acknowledge, look, even if I get no errors, okay, that's the ground truth. No errors are produced. And we acknowledge that the upper bound here could be theoretically as high as this, whatever, it's 5%. And then over time, you can further supplement that with additional data and make that upper bound smaller and smaller over time. But as long as your validation plan up front says, look, here's upper bounds, this is what we're gonna do, this is essentially the power of our analysis, I think that's a good effort in a deployment validation and not having to do those 300 comparisons to get that 1% error rate.
Great, thank you. Todd, I know in your presentation, I believe you were mentioning kind of the pros and cons of having a single individual versus multiple individuals kind of getting trained all at once. I guess in your experience, having worked with a couple different agencies and validations, what has been kind of the most beneficial or the easiest transition for those laboratories?
So when I've talked about it with laboratories, we kind of talk about those pros and cons. And so far laboratories, because we don't have guidance or consensus yet, laboratories have chosen to go with that initially upfront, the one validation manager doing that initial hardware studies. So the one person is doing that initial 30 or 20 measurements and getting those control charts started. Because then the rest of your laboratory staff can just focus on casework, and the one validation manager is focusing on the initial validation studies. So that's the approach that we've used. But like I said, the problem then though potentially is when you start incorporating those other people into your validation studies, you might start getting flyers, and that's the potential weakness. But you have the things with those control charts though, if you have flyers and noise, if you get enough measurements, then your error bars are going to start widening out, but you have a potential root cause. And some of that though, I would argue is competence. Okay, one person's capable of getting these measurements. What is that other people doing? What are they doing that's causing these flyers? And maybe you can further train those people to get their measurements more tight. So that's the approach that has been chosen, but I'm not necessarily saying that's the gold standard, the right way to do it. It's just a way to go about doing it.
No, absolutely. And it's great to know kind of what labs are choosing for themselves in the lack of that current guidance. We still do have a little bit of time. If any of our audience have any more questions, again, please feel free to raise your hand or throw those in the chat. While our audience stews on that for just a moment, I'll kind of pass things over. Alan, Todd, do you have any final thoughts, things you didn't get to in your presentation, or anything you'd like to share as we get ready to wrap up?
My quick thought, I briefly had a line of this. I see a question came in, but real quick is be careful when talking about these error rates. I've gotten a little slapped on the wrist at times from statisticians in that, you might have an error rate and you might, when you go and testify, look, the error rate is whatever, it's 0% or it's 0.1%. You could talk theoretically, this is what we produced from our error rate, this is a study, but that error rate may not necessarily speak to the case at hand. Because that error rate incorporates all of your samples and all, but maybe the sample you're looking at is a lot easier. And so the error rate might be lower than what you calculated. Or maybe this is a type of mark that tends to produce higher error rates. And so you have to be careful about describing it and just be specific. Look, this is the error rate we got from our study that provides some general guidance, but you may be clear, this may not be specific to the specific case at hand. And I think providing that limitation is a good thing to do.
Yeah, there's been a lot of talk of validation and NIST right now. As a matter of fact, they're doing another foundation's report surrounding validations in forensic science. And one of the key topics is something called a factor space, which is exactly what Todd was talking about. If you only validate with Glocks, then technically you're only validated within that group of Glocks, not even Glocks outside of that group, right? So this limitation of what samples you choose and what it actually entails really speaks to how sure you are. And it's funny because they started using DNA black box testing as a way to build this tool that NIST is going to offer eventually, that based on the type of case conditions, you can actually search and filter through and see how many samples have you run in your validation that has this set of parameters. And some of those only has 2 or 3 comparisons, and maybe you're not as strong in your conclusions. But that's why I think overall, get used to the idea that validation is not a solid checkbox somewhere. It's going to be an amorphous thing that changes depending on the types of conditions in your case. Another thing that I'll reiterate, just like Rachel talked about last time, you guys have to take measurements very seriously. These 3D instruments are not, push a button and just walk away type of things. There is effort. The more front-loading effort you do to make sure that measurement is good and perfect, the better you're going to be overall. Because remeasuring things always take a lot more time, and there's no reason for that if you do all the work ahead of time. And being someone who's been measuring these things for over more than a decade now, it's the worst feeling when you run a whole bunch of samples, you go back and you go, crap, I got to measure another 10, then it ruins your schedule for the rest of them. And it really does affect not only VCM. A lot of the stuff that we're implementing now, especially for quality assurance and doing control charts, all of this transfers to future use in algorithms as well. And just like the examiner need nice and clean images to do the VCM, algorithms need even cleaner images to do any kind of calculations, because any of that debris or measurement errors really affect the algorithm. It's going to really affect the score and the overall conclusion from that particular system. So I'm glad to see that there is a push forward in adopting these 3D instruments, and I've been standing on a soapbox for years now saying, get these instruments now, learn how to use them, so by the time we get these tools rolled out like VCM or algorithms, your lab's ready to go. You have your validation done, you have your quality assurance done, you're tracking everything. All you're really doing is plugging in a new algorithm to then use existing data that you already have. So I'm glad that we're pushing that forward. I do think we have new questions.
Yes, we did get 2 questions in. The first one, research-wise, does a single KNM comparison consist of just 2 specimens, A versus B, or does it have to be a set of 3 versus B?
So the twig sets will be 2 knowns and a Q. And that's going to be an open set. And I don't have any preference or any heartburn about just 2 samples per comparison either, if you wanted to go that route. Because then you can really adjust for how difficult you want it to be, right? With the other one, you can choose A or B, or the quality of marks. If you just have a K and a Q, then you really have to, you can tune the difficulty of that test more. But either one should work in this case, because at the end of the day, you're just trying to figure out ground truth.
But to further along Stephen's question, Stephen, just to make it clear, if you have your second scenario, a known, say you have 3 knowns, or an example of 2 knowns versus an unknown, that doesn't count as 2 comparisons. Those 2 knowns versus the 1 known is 1 known non-matched comparison. You're just giving the 2 knowns to essentially act as if there's a test fire, a known test fire. I don't personally have any heartburn of 2 unknowns versus each other, with like the Kiesler study. So that would also count as a unknown, just more like a casework scenario where you don't have a firearm. You essentially have two unknowns versus each other. And that would also consist as a known non-directional comparisons. But the traditional kind of what the consensus is with the whole PCAST report is you have two knowns versus one question, and that counts as one unknown comparison.
Thank you for that important clarification. Can see how that might trip people up, thinking it might be more than one. Another question, when talking about error rates, is that in relation to the results of the algorithm, or is it dependent on the examiner?
So today our discussion is mostly revolved around VCM, right? So in this particular case, that error rate is of your VCM system. So all of your examiners involved and all of the hardware involved and everything else. So essentially, if you're a lab with two instruments, you are quoting your validation study using those two instruments and my 5 examiners, and I have a 0 to 1% false positive error rate. But the same can be done in the future when we start looking at algorithms. It's a little bit different then you're actually just looking at the scores, but then rambling a little bit. But the current path for algorithms right now is not to make an ID exclusion or inconclusive conclusion. The current thinking right now is we're going to give you something called a likelihood ratio. And it's completely different talk and for another time. But in general, it's not going to say that's definitely an ID or this is definitely an exclusion. It gives you a weight of evidence on a sliding scale. And what that looks like remains to be seen. We're doing some research to see what it looks like in comparison to human conclusions. But everything we talked about today is purely VCM and dependent on, and it's not so much dependent on the examiner, it's dependent on your system. But there was some talk when we were discussing this when it comes to validation as a whole. The more testing you do as an examiner, the more you build your own pool of data showing how accurate you are using the system as well.
Great, thank you for that. I believe that just about brings us to the end of our time. So unfortunately, if there are no further questions, we are going to go ahead and wrap up today's webinar. Please feel free to contact our presenters. Their information is going to be going up on the screen here. Thank you for your patience. Thank you so much for attending, and we will see you all again next week for session 3. Titled Casework Efficiency, LIMS Integration, and Workflow Configurations. Thank you.
Thanks, everyone. See you all next week.